Hello and welcome back, and today we answer a confusing question. That is, why do we use angular frequency or omega in simple harmonic motion when nothing is actually rotating? You see, the mass moves in a straight line, yet the math looks like circles. In this lesson, we'll see how circular motion acts as a perfect hidden code to unlock the physics of simple harmonic motion. So let us start with the simple concept of frequency, that is the number of cycles completed in 1 second. So let us slow this motion down, and we see that at time t equal to 0, when we release the spring, the mass springs to the left, and if we wait for 1 second, we find that the mass completes exactly 5 cycles. And we say that the frequency of this vibration is 5 Hertz. And here 1 Hertz means 1 cycle per second. Now let us ask the next natural question. If the frequency is known, what is the time period? Well, the time period t is simply the time taken to complete 1 cycle. So here, if it took 1 second to complete 5 cycles, time required to do 1 cycle is nothing but t equal to 1 second upon 5, which is 0.2 seconds per cycle. So the time period is 0.2 seconds. And you can immediately see the relationship. F is equal to 1 upon t and t is equal to 1 upon f. That is, frequency and time period are reciprocals of each other. Now let us move to something more conceptual, and this part often feels confusing at first, but stay with me and you'll find that it can be very visual and simple. So what if I say that 1 cycle of this back and forth motion can be represented by motion on a circle? At first that sounds strange because the mass is moving in one dimension only, left and right, but then notice we are not saying that it is moving in a circle. All we are saying is that can we use circular motion as a reference model to understand a simple harmonic motion better? So let's look at this setup. When the mass is at the extreme right position, that is plus A, we represent it by a dot on a circle, also at the extreme right. Now keep an eye on this dot. It's small but important. Then as the mass starts moving to the left, the dot starts moving around the circle. So now two things are happening simultaneously. The mass moves in a straight line. The dot moves uniformly around the circle. Now let us watch what happens. When the mass moves from plus A to minus A, it completes half a cycle of SHM. At the same time, we see the dot moves through half a circle, which corresponds to pi radians. That is, if the entire circumference is 2 pi radians, half a circle is pi radians. Now let us allow the mass to complete 1 full cycle, that is back to plus A, and what you will notice is that the dot has completed 1 full circle, that is 2 pi radians. So we learned something very important here, and that is 1 complete cycle of SHM corresponds to 2 pi radians of circular motion. Now it is simple. If the mass completes 2 cycles, the dot completes 2 full circles, that is 4 pi radians. If the mass completes 3 cycles, the dot covers 6 pi radians. So we can say in general, number of cycles into 2 pi is equal to angular displacement in radians. And you see, this allows us to convert linear oscillation into an angular description. So now we are ready to define something new. If the frequency of the mass is f cycles per second, then in 1 second, the equivalent angular motion would be 2 pi into f radians per second. And this quantity is what we call angular frequency, denoted by the symbol omega, where the units of omega is radians per second. So remember this clearly. F, or the frequency, counts the repetitions, that is, how many full cycles happen in a second. Omega, or the angular frequency, measures the angle, that is, how many radians of the reference circle are covered in a second. They describe the exact same physical speed, just using different units. One speaks in cycles, the other speaks in radians.